On April 16th, Rosa Lamarca, Alex Sanchez, Javier Lopez, Montse Guillem, and I discussed the p-value. To explain exactly what the p-value is, I will go over the concepts of conditional probability, power, and support of the hypothesis. I will distinguish between Fisher's concept of evidence and Nyman-Person's proposal for deciding. I will comment on a possible abusive use of P and what alternatives we have for considering the uncertainty of an unrepeatable study. I will end by questioning whether all of this has had any influence on the lack of reproducibility of scientific papers. Let's start by reviewing the concept of conditional probability. Suppose we play soccer with these friends. Among them, 6 out of 10, 60%, wear glasses, and 4 have long hair, 40%. We want to know what information each variable provides about the other. If we know they are wearing glasses, how likely is it they have long hair? Of the 6 with glasses, 3 have long hair, 50%. And if we know they have long hair, what is the probability of their wearing glasses? Of the 4 with long hair, 3 wear glasses, 75%. These are different numbers. They have the same numerator, but a different denominator. With the conditional probability notation, we will represent them differently. After the vertical bar, what we know, and before, what we ask ourselves. In an example by Stephen Sen, the probability that a Catholic will become Pope is almost 0, but the probability that the Pope would be Catholic is 100%. And down we reach our goal. The American Statistical Association statement, in its second principle, says that the p-value does not speak of the probability that a hypothesis is true. There are 2 conditional probabilities that are confused. Let's see both. In this table, the rows represent the unknown scenarios, in other words, the hypothesis. The columns indicate the results that are conveniently dichotomized and lead to 2 different actions. One thing is the probability of the column given the row, and another is the probability of the row given the column. The first quantifies the probability of making a wrong decision if the null hypothesis were true. The second is the probability that the null hypothesis is true once the decision is made. Once again, the denominator has changed. The second point of the statement highlights that this second conditional probability is not the p-value. Let us remember first that the processes for deciding and obtaining evidence are not the same. In this article, Hubbard and Barreri tell us that p and alpha are different measures. In the same way, we will never say that 80 kilograms is less than 180 centimeters, we should not say p is less than alpha. According to these authors, Fisher wanted to answer a knowledge question from the perspective of science. What do I know? While Nyman and Pearson wanted to help in deciding by limiting the possible probabilities, risks, of choosing wrong actions. Let us emphasize that the decision calls for a cutoff point at which we will act differently. For example, if a patient exceeds so many points on a certain scale, we will take him into the operating room. This cutoff point marks the threshold from which the decision changes. Remember, p's and alphas are different measures. But knowledge does not require this. The evidence can be a continuum without highlighting any limit, neither 0.05 nor any other. Simply stated, the lower the p, the more evidence against h. This implies the greatest limitation of the p-value. Acquittal does not imply innocence. Or more formally, absence of evidence does not imply evidence of absence. Let us now see the power or probability of obtaining a significant result if the alternative hypothesis of interest were true, and the support in favour of H or support of the evidence accumulated so far. And we are going to see them with the computer application referenced here, which can be accessed by the viewers. This paper shows how alpha, power, and support altogether influence subsequent credibility, which we define as the probability that the effect will be true once a significant result has been observed. The left column in blue indicates real effects, while the one on the right in pink represents those that are false. In this example, we put high values for support and power, and we keep alpha to the traditional 5%. As the expectation of the effect is high, 75%, the left column is 3 times thicker. In addition, the upper part of the graph shows the results that are statistically significant, while the lower part has those that are not. As the power is high, 80%, most of the results at the top of the first column are significant. And since alpha is 5%, 95% of the results in the right column will be non-significant below. Thus, when we gather all the significant effects in the lower quotient, we see that 98% comes from real effects. This is good, very good. The hypothesis test with support and power works. In this new counterexample, we lower the support to 20% and the power to 10%, although we leave the significance limit at the same 5%. Now the true effects within the significant results falls by up to a third. 2 out of 3 p-values will come from situations where the effects are not true. That is, without support and without power, the p-value alone becomes a lottery. Regulatory agencies know this. The figure represents the previous studies that support the hypothesis. The Phase 3 RCT is then sized to guarantee its power. Regulatory boards require both support and power in order to authorize a new drug. Have we abused the p-value? Do we do significant tests without power and without support? That's for you to decide. However, we do have alternatives to the value of p. The Consort Guide for Reporting the Results of Randomized Intervention Studies, which was published last century, asks researchers to report the magnitude of the effect accompanied by the compatibility intervals, and it also asks that p orphans not be reported. Let us remember that the fundamental principle of science is reproducibility. However, in the field of medicine, Paul Glasneau and the creator of Cochrane, Ian Chambers, have estimated that 85% of investment in research does not end in replicable studies. Has using a measure as cryptic as the p-value contributed to this waste? This seems to be the opinion of the editors of Basic and Applied Social Psychology, who banned the use of p-values in their magazine. In short, don't use p's without support and power. And avoid orphan p's. But let's state it positively. First, add intervals of uncertainty. Second, indicate the measures of the degree to which you want to achieve your objective, i.e., if you want an intervention, report the effect size. And third, follow the reporting guidelines. As a reward, your impact will increase. Thanks to Professor Joan Garcia and to all of you for your attention, and to my friends Professor Jose Antonio Gonzalez for the shiny app, and to the cartoonist Enrique Ventura for his illustrations. An elderly Goya titled his self-portrait, Aún aprendo, I am still learning. We apologize to all of you that we had previously explained the p-value without highlighting its limitations.